Number 6. 4.3, numero 60. I don't speak whatever language I just made up. I'm going to put that on the floor. I'm going to steal John's homework because it's right here. Number 6. Shh. Yes.
Did you do all of it? Because I was doing
all of number 6?
Yeah, acceleration of the system.
Okay, number 6 is great because it's exactly what you're doing in the lab. So here we go, number 6. So number 6, you're given this. You're given a block here that has a mass of 5 kilograms, and you're given a 1 kilogram block here, yes?
0.25.
Oh, is it 0.25? Is that small?
Yeah.
What problem am I thinking of? All right, are those numbers right now?
Yeah.
Yes.
Okay. So notice, big mass, little mass, attached by a string, yes?
Yes.
All right, so question A says what? Honest question, I don't have the sheet.
Find the acceleration of the system.
Find the acceleration of the system. Okay, so when it says the system, it means the 5 kilogram and the 0.25 kilogram masses combined, right?
Right.
So let's identify the forces. Is there friction?
No.
Ooh, well, that's nice. So there's going to be gravity here. Guys in back, shush your face.
Wait, Mr. Hudson?
Yep.
Is it supposed to be negative, or did we decide what way it's supposed to go? Or is it?
These ones, it doesn't matter because they're going to cancel out anyway.
What do you mean?
Because there's gravity and a normal force.
Oh, got it.
Right, the 5 kilogram thing is sitting on a surface, right?
Oh, right, okay. So it's the hanging ones or something?
So the hanging one is what produces the acceleration.
Oh, okay.
Oh.
Got it.
Good. Was that too hand-wavy? Do you guys see what I'm saying? I know what you're asking. What I'm saying is I haven't yet decided which way is going to be positive and which way is going to be negative. Because the motion is going to be in one of these two directions.
Yeah, no, but then why is your force of gravity, is your force of gravity negative?
So whatever. I didn't even think about these negatives because as I was writing it, I was thinking, oh, well, gravity's pulling it down, but there's going to be a normal force holding it up. I know they're going to cancel. I know they're not affecting the motion. See what I mean? So they don't even really contribute to the motion at all, so which way is positive and which way is negative is kind of irrelevant here. Good?
So when you're calculating the acceleration, is that the reason that you don't include like force of gravity of A?
Yep, that's exactly why.
Okay, but you include the mass of
Because, yeah.
the mass of the system.
Yep, because, so this, you guys, this is exactly what we're doing in the lab tomorrow. This is the cart, and this is the hanging mass. And we're assuming that the track is frictionless. So this is literally what's going to happen in the lab tomorrow. So everybody good up to here?
Yeah.
Does everybody understand why these cancel and why I'm going to not worry about them?
Yes.
All right, so all I really care about is this force of gravity on my hanging mass. So 0.25 times 9.8 gives 2.45 newtons. Now we got to decide if we want to make it positive or negative. It's arbitrary, but since all of our motion is going to be this way, let's make that way positive. And I would strongly encourage you to do the same thing tomorrow. Okay? So it's going forward and down. Okay? You guys know what I mean? All right, so is everybody good up to there? All right, are there any other forces on my system?
No.
Why don't I worry about tension?
Because it's inside the system.
It's an internal force. So, acceleration of the system is net force of the system over mass of the system. Net force is 2.45 newtons, and that tiny force is responsible for accelerating the whole system. So what mass do I use? 5.25. What's up, Ray?
Why don't you, like for the last for 7, you use calculate the force of gravity, and then why don't you do it?
So the last one was, I don't want to set it up again, but you just had two things suspended in the air. Right? Why isn't the 5 kilogram thing going to fall?
Oh, they cancel
it's sitting on a table, right? So there's a normal force supporting this. Does that make sense?
Yeah.
Everybody good?
Yeah.
Okay, cool. So that's the acceleration. So divide this out, and the acceleration of the system ends up being whatever that is. Anybody know? 0.47. Okay, so that's part A. Problems. All right. Does part B hopefully ask for the tension of the rope?
Yeah.
Yes.
Excellent. So, are there questions with A before we do B? Okay. Yeah. Shoot.
So, you find the force of gravity at the hanging mass, and the big box A doesn't matter because it's like the forces don't matter because they're like they cancel out.
Exactly so.
But you still add the mass to. You still add the masses of both boxes.
Do you see why? Because the whole, I wish I still had my track set up here, but when I release it, gravity's going to pull this dude down, which in turn is going to pull this dude forward, right?
Yeah.
So, like, if I cut the string, then the little weight's just going to fall at 9.8 meters a second squared, right? But that's not what happens here, because this force of gravity isn't just making the weight fall, it's also pulling this giant 5-kilogram thing forward. You see what I mean?
Okay.
Cool?
Yeah.
Everybody good?
Yeah.
All right. So let's find our tension. So to find the tension, oh, shoot. So the acceleration of the system, we just found it was 0.47 meters a second squared. All right, tension. We got to pick an object. What object do you want to look at? The small one?
Yeah.
Okay. I probably would have picked the other one, but it doesn't really matter. We're going to do them both anyway.
I got a question.
Yeah.
That force is 0 on the other one, so that's why I want to pick that.
Say it again.
If you pick the 5-kilogram one, wouldn't that force just be 0?
The net force on the 5-kilogram one can't be 0 because its acceleration isn't 0.
Oh, because you have to add like.
What pulls the 5-kilogram thing forward?
425.
Name the force, not a number. Name it.
Tension of the.
Tension, right? Do you see what I mean or no?
I know what you mean.
Okay, so we'll do that in just a second. All right, so, but you said the little one, so let's do it. 0.25 kilograms. So, force of gravity is negative 2.45 newtons. Tension is holding it up with some amount of force. We know our acceleration is 0.47 meters a second squared, sorta. Negative, because it's going to accelerate this away. Yes? And so our net force is mass times acceleration, so that's going to give us negative 0.1175. Is that right?
Yes.
Newtons? Good?
Yeah.
And so now net force equals Ft plus Fg, so we got to solve this thing. So let's see. Our net force is negative 0.1175. Our tension, we don't know. Our gravity is negative 2.45. Add it, and your tension turns out to be 2.33, basically. Is that right? I did the math in my head, so still good. All right. Questions, you guys? All right. So that was not bad, was it? It was just two forces to deal with. All right. Let's check our answer by using the 5-kilogram thing. Yeah, Abby.
So I'm still a little bit confused. So it's like the signs of the system are what you decide are either positive or negative. But when you take each component of the system, then it's just regular force of gravity is always negative, normal force is positive.
Exactly. Yep. So this sign convention only corresponds just to this system. And it's basically just a way for us to decide whether the forces are working with each other or against each other.
Okay.
Okay? So when I found this acceleration here, Abby, this 0.47 meters a second squared, that was the acceleration of the system, and I knew that it was going to accelerate in a positive direction, so this way.
Right. 'Cause that's
Right?
what it's
But for gravity, I mean, for the green thing, it's accelerating down, which is negative, and for the 5-kilogram thing, it's accelerating forward, which is positive. So that's why those sort of contradict each other. So that's why we need that that highlighter blue definition.
And this is just a general question about tension. Is tension always operating positive?
No. I mean, usually when you say what's the tension in a thing, you give a positive answer. But like when I pull the wall, there's a force at both ends and they're in opposite directions. So one of them has to be negative, sort of, you know?
Yeah, okay.
You know what I mean?
Yeah.
All right, everybody good?
Yeah.
Okay, so let's look at the 5 kilogram thing. So here we go. Here's our 5 kilogram thing. What forces are on it? Well, gravity, normal force, I don't care, and what else?
Tension.
Tension. Follow? Is that it? Oh, and we know the acceleration is 0.47 meters per second squared, right? Good? So our net force should be mass times acceleration. So 5 times 0.47 gives 2.35? Darn it. Just nothing. We got screwed by rounding. All right. So if our net force is 2.35, that means our tension force must be 2.35, right? Because that's the only uncanceled force, right? Okay. So the first time we got 2.33, here we got 2.35. That's just a rounding issue. Cool? All right. Questions on that, you guys? All right. Was there a part C? I think there was, wasn't there? No.
Yes, there was a C and a D.
Okay, so what is C? Is that friction, maybe?
No, C is figuring out something about time.
Ooh.
You have like a displacement and you have to figure out a time. It's just plugging in.
Okay. Do we need to go through that?
Once you've figured out like the acceleration, everything else is pretty self-explanatory.
Okay, well, we had a request for D, so let's do it real quick. So what does C say?
Assuming both boxes start at rest, how long will it take for box A to reach the edge of the table? 50.5 meters away.
Okay, so what it's telling you then is that box A, sorry, this is part D, box A, the edge of the table is, what did you say, 0.5 meters away?
Yeah.
So what's that a measure of, you guys?
I'm sure
Did you get it?
I'm good on that.
Okay. Does anybody want me to go through it? I'm happy to.
Yeah.
Yeah? Okay, so what's the 0.5 meters?
It's the displacement.
Displacement, right? It says both objects start at rest, which means VI is 0, and our acceleration is 0.47 meters a second squared, right? Good up to there?
Yeah.
And it wants to know the time, right? Sorry, I swapped sides on you. So I think, I don't know why, so now I think we can just use this guy. Delta x equals 1/2 AT squared plus VIT. Since VI is 0, this part goes away, and you solve for time, and you get whatever the answer was on the sheet. Is that cool?
Yeah.
All right, what's D then? Sorry? Find the coefficient of kinetic friction that what?
I think it's actually C.
This is oh wait, no.
Oh, that would keep it at rest? Ooh, that's a good question. We have time to do that. All right, so let's do part, oh, this was, damn it. This was part C, now I'm doing part D. So part D says find the coefficient of friction that keeps it at rest, is that right?
Yeah, you're finding it.
So look, this is actually not that bad, guys. Look, here's the pulley. You got a 5 kilogram thing, right? Gravity's negative 49. Normal force is 49. Your force of gravity here is 2.45 newtons, right? And we've still got that, right? Now, if we want the system to not move, then that force has got to be 0. What's going to prevent the system from moving? Static friction. So how much static friction do we need to prevent it from moving? 2.45. Oh, damn it. 2.45 newtons, right? Good? So then you know your normal force and your force of friction. So FFS max equals coefficient of static friction times normal force. So 2.45 equals coefficient times 49 newtons, and divide it, and you get, what is that, 0.05? Is that right? Cool? Cool. All right, the bell's going to ring here in a minute. So here's the deal. Tomorrow's lab day. I don't think the lab's going to take you the whole hour. So if you guys have other questions that we haven't resolved today, I'm happy to answer them. Also, if there are problems that I didn't do here that you wish I would have done, I'm going to try to do a different problem in 7th hour. I did number 5 in 5th hour. So they're up there. Okay?